Today we're going to look at simulation and optimization. While there are great offerings through the Solid Edge ecosystem for in-depth simulation analysis, Solid Edge simulation is all about analysis for the design engineer. CAD Integrated, easy-to-use tools providing accurate results so that you can virtually test your design. Is it strong enough, or is it too strong and wasting money? Solid Edge simulation offers a lot of great functionality for users with varying needs. In the first look, we took a look at running a simulation study on a part, but what about our assemblies or other types of geometry such as frameworks and sheet metal? For the next 15 minutes or so, we're going to be looking at several great capabilities in order to give you a good understanding of how to work with several different types of geometry using Solid Edge's tools. The first thing we're going to look at is beam analysis. Beam analysis is a great tool inside of Solid Edge simulation for users who design frame structures. Here we have an engine hoist that we need to ensure is properly designed to hold our target weight. This means ensuring strength, as well as ensuring that it's not over-engineered. Using beam analysis is a great way for designers to quickly validate the strength of their parts without the cost of added time and resources to analyze complex shapes and features. You can see that with Solid Edge Simulation's simple interface, completely integrated within Solid Edge, creating simulation studies are a breeze. For our engine hoist, we just want to ensure that our frame members can stand up to the 20,000 Newton force that it's rated to support. While setting up beam analysis, the first step is choosing what parts are going to be analyzed. For beam analysis, only frame members are going to be selectable for the simulation study. Solid Edge also offers us the options of creating forces on a single point, such as the node on the end of this frame, or a distributed load across the entire length of the frame. For both of the forces and the constraints for this model, we're going to create point features for a more accurate representation. Also recognize that these tools are intuitive on how this machine will actually work. We put the force load at the location where the load will hang, and we fix our model at the points where the frame meets the casters on the floor. Now we just need to constrain these 3 frame pieces to the base so that we have a realistic representation of how this will behave under stress. Once fully constrained, we simply need to mesh the part to solve the simulation study. Meshing on a beam analysis is very fast and efficient, as Solid Edge simulation doesn't need to worry about the exact geometry in order to get a great approximation of the reaction forces on its members. This is a huge benefit, especially when solving simulation studies on a very large framework assembly. Notice on our stress plot the colored representations of stress concentration. Using our color key, we notice the red area is the location with the most stress, but still well below our breaking stress or yield stress of 380 megapascals. However, another great use for Solid Edge simulation is to check to see if we're overbuilding parts and spending more money than we need on larger stock. Here, if we look at these 2 frame members in the back, we can see that they have been overbuilt and the amount of stress being placed on them does not warrant the size of the tubing. A quick edit of both of those frames is made easy by simply selecting the components that you wish to change, editing the definition, and then verifying that that's what we want. Solid Edge framing allows you to either use a set of delivered standard frame sizes or define your own custom frames and materials. Here, we're going to use a DIN standard tube that's going to be slightly smaller than the one that was previously there. Solid Edge has great indicators of when geometry is changed or when a study needs to be rerun using our status indicator on the edge bar. Now that our new framework is in place, we can simply resolve the study that we had set up before without having to take any additional steps. Viewing our results from the change we made, we can see that these tubes are more appropriate than the previous as we're still well under our yield stress. If we need to make further inspections on the results, Solid Edge provides us with tons of great tools to be able to either probe the model to see what's taking place at a specific point, or to simply turn on our maximum or minimum markers to point out areas of concern of maximum stress or displacement. Now that we know that our framing on the main hoist assembly is appropriate, we need to take a look at a leveler that we're going to be supplying alongside with it. Another great thing about solid edge simulation is that you can have several simulation studies set up at the same time, depending on what it is that you need to be validating. As we take a look at our leveler, we'll use a clipping plane to see the internals of the part. We can see that we have a threaded bolt running through an adjustment bracket to control the balance of the engine being held. This is going to be an area of concern for our next study because if the bolt is bent, then the leveler isn't going to work properly. Now that we know what we're working with, let's take a look at some more of the great tools that solid edge simulation has to offer. To start, we're going to represent these two welded sheet metal end caps as mid-surfaces. We know the sheet metal caps are strong enough to hold the weight, so we'll use this as a lightweight representation for a more efficient study. Once our surfaces have been created, we just need to set up the simulation study to incorporate both of our surfaces as well as our solid bodies. Using the mixed and general bodies option when setting up the mesh allows us to do just that. The first step in our study setup is to pick all of the geometry that we need. Since the bolt isn't meant to be load-bearing, we'll just leave it as a point of reference. Now that we have our geometry, we need to set up the rest of the study. Keeping consistent, we'll do this by following similar steps as the beam study. The first step is setting up our load. Since the weight will hang off of both sides of the balancer, we will distribute the 20,000 newtons between both of the holes in the surfaces that represent the sheet metal end caps. Next, we'll set up our constraints. The rollers in the model have a slight plane on top to represent contact between the sling arm and the rollers themselves. Using solid edge selection options makes picking this up as a single feature both quick and efficient. Fixed constraints set, and now it's on to making sure that solid edge simulation knows how all of these individual parts should fit together for the study. These connectors will represent how the parts are held together. We have several connection options, such as bolted, edge, and manual definition. One of the best time-saving options in solid edge simulation is the auto connection command. We'll simply select this, set our distance far enough so that our mid-surfaces are picked up, and then set all of the parts as glued. You'll see just how quickly solid edge picks up all of our contact points between the parts and then sets the connectors. Now that our study is properly defined, we'll do a mesh and solve. For our meshing options, we have complete control over what we want for both solid and surface mesh settings. However, for this study, we'll keep the default values chosen by Solid Edge, as they've been chosen to ensure the best results. Notice that our solve time is still very fast using some of the tools, such as the mid-surfaces for the bracketry. While it looks like the balancer is nearly folded over on itself, this is just an embellished representation so that you can understand how deformation will occur. To view the real deformation, we can simply change it over using the actual representation option, and what we're mainly interested in is not stress distribution, but displacement. We need to make sure that our part doesn't bend to the point where the adjustment bracket can't travel up and down the bolt threading. To see this, we can animate exactly how the part will deform as it is loaded. Our bolt shows the original position, while the animation shows how much flex there will be in the leveler. Here we'll notice that the deformation is nearing 8 millimeters, which is too much for this assembly. We have a requirement that deformation cannot be more than 1 millimeter when fully loaded. Of course, working inside of Solid Edge with synchronous technology allows us to make any geometry changes we'd like in order to figure out the best solution to ensure that our deformation isn't too high or that our parts aren't too heavily overbuilt. We can simply input whatever values we wish to try for the dimensions and then watch the model update accordingly, all while keeping association with the simulation study features. However, rather than manually making changes and rerunning the study each time, Solid Edge Simulation offers a wonderful tool that takes all of the hard work out of optimizing your designs for simulation. I introduce to you Simulation Optimization. Now to start, we need to define an objective in which we're trying to reach through the optimization. For our design, we're trying to reach a target deformation of 1 millimeter for maximum deflection. Secondly, we need to add a limit to make sure that we stay within the boundaries of what our part can handle. Our limit is going to be based on not exceeding a certain yield stress, and we'll make sure that the assembly stress must stay between 0 and 190 megapascals. Next, we need to add the variables in which we want to change the model. These variables can either be from the top-level assembly or the parts making up any of the subassemblies. Here, we're going to solve using two possible options, the overall length and the thickness of the beam. Also notice that all of the other pertinent variable properties, such as the associated ranges, come along with it. For the remainder of the options, we're just going to keep the default values, but basically they're going to control the maximum number of iterations as well as settings to say when the study has officially been solved. Once we begin our optimization, we see that as it iterates, it's going to take the values of each subsequent study and narrow down what the most optimized condition will be. Just imagine how long it takes engineers who don't have this tool to do it. Of course, depending on the input settings and the level of precision that you're looking to find, it might take a little bit longer. As the optimization is running, this is a great time for us to work on other tasks, or maybe just go and get a cup of coffee. Because in the end, Solid Edge is going to provide you with a very nice summary of everything that's been found and all of the associated values. Also, certainly worth noting, the underlying engine that's driving the simulation is FEMAP and Nastran, which is industry-leading simulation technology. So we've got our summary printed out in Microsoft Excel, which means we could easily send out or use this data for whatever purpose. Here, we've seen that the Optimize solved our problem for us, and we're ending up with our needed values of what we need for our final dimensions of the beam. Seeing as these decimal values aren't likely to be stock, we'll just round and say that we're good to go with a length of 700 millimeters and a thickness of 5 millimeters for our beam. Taking a look at our final iteration results, we can now use any of the other tools to report our findings. Another quick animation to ensure that we're not exceeding our deformation limit of 1 millimeter, and I think we're ready to generate our report. All of this information, including the animation, can be saved out for use on design reviews, marketing materials, or any other use that you might find in your design workflows. Report generation is created the exact same way that we did on the part for the Master Mover that you saw during the first look demonstration. However, to show you the detail contained within it, we have a copy of a report on our engine hoist that has already been generated. This report tool is great because it automates all of the value outputs, including the results, images, values, and organization structure of the report. As you can see, Solid Edge simulation is a dream come true for design engineers. From making sure that your designs are appropriate for their purpose, which means that they're strong enough as well as not over-engineered, having the capability to use different methods to get efficient results, to a full optimization capability that can solve multiple variables with minimal designer input. Solid Edge simulation truly provides a full and valuable solution for your simulation needs.